Hello and welcome to my video lesson 1.2 on impulse. Impulse is a change in momentum. So last video we talked about momentum, which is, I'll actually write that formula out right here. P equals mv. But impulse is the change in momentum. So not this formula, but instead this, which is the final minus initial. Okay, so impulse is the change in momentum. Impulse is also a vector. It comes from the vectors of the momentum itself, and it will always be in the same direction as whatever force is being applied. So impulse is one of the only situations, really. Well, it is the situation where energy is not conserved and momentum is not conserved, because you're looking at one portion of the system, and in the entire system, yes, energy is conserved and momentum is conserved, but you're zooming into only one part of it, which is why when you zoom in, the momentum is changing. So, for example, if you hit a golf ball, the golf ball will speed up and go from 0 to some fast speed, like I think I was Googling it, and it's like 80 meters per second. It's pretty quick. So it'll go from 0 to 80 in a short period of time, and that is the impulse that the golf ball is feeling. Okay, but if you zoom out, where's the opposite reaction? On the golf club, right? The thing you hit the golf ball with, it's on there. So if you zoom out far enough, yeah, there is no impulse, but impulse is the change in momentum, and if you look at a specific object, usually that's what we're talking about. So yeah, since matter cannot be created or destroyed, the only thing that can change to make the momentum change is the velocity. So if you look at this formula here, the velocity has to be changing. So what we sometimes will write is delta P equals m delta V. Okay, or there's also one more interesting one, which is coming from right there, force times time. Okay, so usually what we're going to do is just use this formula, which is to put both parts together. The definition of impulse, this is kind of like the definition. And this is another equation for it. So we usually will put these two things together. And yeah, let's think about this for a little bit. While we think about that, the area under the graph is the impulse. Well, why is that? This graph is not showing it. This is time here. So it's not showing it very well. But basically, if you look here, delta P equals F times T. Okay, so delta P is your change in momentum. That is the impulse. Okay, and that is, in this case, Y. Oh, no, sorry. No, in this case, sorry, Y is your net force, and X is your T. But what you can see here is that the area under the graph is going to be the impulse, because how do you get area of a rectangle? Length times width. What's the length here? Well, it's the bottom, so it's T. What's the width? It's the side, so that is F. So F times T is delta P. So that's where it comes from. It's the area of the graph is length times width, so that's why it gives us the delta P. I was thinking slope there for a second. Alrighty, so let's just think about this formula and how it applies to us. Considering the formulas above, how do airbags and crumple zones keep us safe in the case of a car accident? Well, as always, I recommend you pause the video, you think about the question, and you press play once you feel like you have an answer. But I will answer it at this point. So airbags and crumple zones, how do they keep us safe? Well, they can't really change the mass of who you are, right? That's still what it is. And they can't even change the delta V. Because you're going from, let's say, 30 kilometers an hour to 0 kilometers an hour pretty quickly. Okay? So the delta V doesn't change. But what they can do is they can lower the force on your body. So the impulse stays the same, but the force can lower, and therefore, so they must increase the time. So the impulse is the same. They can't change this. It's the same no matter what. Like we can't adjust that. That's for this whole thing. Okay? But what we can change is we can change the time. We can control. How would you control this? Well, if you increase the time, then the force must decrease. So if you have, if you go from 100 kilometers an hour down to 0 kilometers an hour, and it takes you 30 seconds, you know, that's you stepping on the brakes pretty quickly, but not that bad. Okay? If you go from 100 kilometers an hour down to 0 kilometers an hour, and you do that in 5 seconds, you might have whiplash. Okay, it'll be pretty darn fast. If you go from 100 to 0 in half a second, you're probably dead. Why? Because the force is too high. So what we want to do in the car is to somehow make that time increase. So what the crumple zones do and the airbags do is they increase that time component. They take that over a longer period of time that you slow down as your face is going into the airbag, as the car's front is being compressed. That is slowing you down more slowly than if it all happened instantly. So because, so we increase the time in order to decrease the force. Alrighty, so let's continue on and take a look at some calculation sort of questions, okay? A Falcon X, SpaceX Falcon 9 rocket has a mass of 506,000 kilograms and a payload of 13,100 kilograms. When taking off at the first stage, has that much force of thrust over 180 seconds, while the second stage has that much force over that many seconds. Which of these stages has greater impulse? Okay, so let's go ahead and try this out. It's not going to be perfect because some of the thrust comes from the rocket actually ejecting matter down, and so it will have decreased mass by the time the second stage kicks in. But we're going to just ignore that for the purposes of simplicity. So stage 1 is going to be delta P equals Ft. So in this case, delta P equals 5,900, but it's kilonewtons, so we're going to do 1, 2, 3 to times it by 1,000 newtons, times by the time, which is 180 seconds. Okay, and we can get the answer for that. So 5, 9, 1, 2, 1, 2, 3 times by 180 So we get 1.062. Let's see, we've got 3 sig digs. So 1.06 times 10 to the exponent 1, 2, 3, 4, 5, 6, 7, 8, 9 kilogram meter per second. Okay, now we're going to do stage 2 of the rocket, which is going to be the same basic calculation. Delta P equals Ft. So delta P equals 801,000 newtons times by 375 seconds. So 801,123 times 375, and we get 300,375. Oh, let's just simplify that to 3.00 times 10 to the exponent 1, 2, 3, 4, 5, 6, 7, 8 kilogram meters per second. So quite a bit of impulse onto both of these rockets here. Okay, but what you're going to find if we just continue the question a little bit, if we ask the question, what is the acceleration on the rockets, you're going to find that that's actually not too big, because the mass is also very big, or at least it's not as big. Still going to be a pretty good acceleration, I think, but not as big. So which of these two stages has greater impulse? Stage 1. All right, let's take a look at the next one. A golf ball is hit by a metal club, imparting an impulse of 4.95 kilogram meters per second, and ends up traveling at a speed of 107.8 meters per second. What was the mass of the golf ball? Okay, so since we know the impulse, okay, that is known, and we're just looking for delta V. Yeah, so we're just going to use this formula. So we're going to look for the mass. So it's going to be delta P over delta V equals the mass. Okay, now we can plug it all in. So the impulse was 4.95 kilogram meters per second. And then the delta V, now this is not necessarily super clear, but it's final minus initial. This is the final velocity. What was the initial velocity? Well, 0, right? When you hit a golf ball with a metal club, it starts at 0. So final minus initial, but it's minus 0, right? So it's just final, right? So we're going to use this. And we can solve that. 4.95 divided by 107.8. And we should have 3 sig digs. So 0.0459. What are we looking for? Kilograms, which if we convert that to grams, it's 45.9 grams. So either of those answers is fine. Okay, just a little bit more. Let's try out this last question here, part A and B. So this one says, the graph below shows the force acted on a particle over half a second. What is the impulse that the particle experiences? So we have to think about our graphing, which is that you're going to use your triangle rule. So triangle, because we're looking for the area, area is base times height. divided by 2 for a triangle. So the base is going from here to here. So the base is 0.4 seconds. And the height is going from here to here, which is 100 newtons. So base times height divided by 2 is what we're going to use here because it's a triangle. If it was a rectangle, you just use length times width. Whatever shape it is, if it's area, just find the area. Okay, so this is going to be 50 times 0.4, 40, so 20 should be our answer, I believe. Now I just want to double check. Yep, 20. And this, you could say Newton seconds, but that's the same thing as writing it like this: kilogram meter per second squared times seconds. Well, seconds squared divided by seconds divided by seconds squared means that those are going to cancel, and that's what we're left with. So I prefer this set of units. If you do Newton seconds, that is allowed, but I prefer those units. Okay, let's take a look at the part B. If the particle was an alpha particle starting at rest, then what was the speed of the particle after 0.4 seconds? I wonder if this is going to be a possible answer, or if this is way beyond the speed of light. You know what? I didn't check this one. I'm guessing it's going to be way beyond the speed of light, but let's go ahead and take a look. So, delta P is m delta V, because it starts at rest, so it's going to be delta P, where it's mass and then velocity final minus initial, but initial is 0. So it's going to be mass 20. Oh no, it's going to be pretty slow then. No. 20 over here, 20 kilogram meters per second. This is like minus 0, right? VF minus 0. So we're just going to actually go like this. I'm going to leave this as delta P over here so that we don't have to write the number a bunch of times. And so we're going to divide by m. So yeah, we're going to have way too big of a number. But that's okay. So 20 kilogram meters per second over, and then 6.64 times 10 to the negative 27 kilograms. We're gonna have to think about how to make that a better question. But for now, this is what we have. So let's go ahead and just plug it in. We're gonna have way too big of a value, not a possible number. So 3.01 times 10 to the 27. Like, I don't know if you guys remember, but this is the speed of light times 10 to the 8 meters per second. This is impossible. This is way too fast. Okay, well, that's okay. It doesn't really matter. The calculation's the same regardless. I just wouldn't make this on a test. I would make this a much bigger mass. Or I would make this a much smaller impulse. Either way that you do it would fix the problem. Okay, thank you for watching. I hope this video helped, and good luck.